Today, mankind stands at the dawn of a new era. A celestial frontier awaits as a technological revolution cracks the final barriers to affordable space travel. The potential reward has ignited a new race for space, a competition based on commercial opportunity rather than national pride. To meet the challenge, pioneers throughout the world are looking to a new generation of spacecraft, exotic designs unlike anything seen before. Wings of tomorrow, which will carry us from a new orbital oasis to the desolate vistas of Mars and beyond. It's a familiar sight along the sun-soaked coastline of Cape Canaveral, Florida. The space shuttle, our link to the heavens, roars skyward. For years, the shuttle has stood proudly as the vanguard of NASA's space program. Yet in the dawn of a new century, its retirement is close at hand. Each time the shuttle takes to the heavens, 240 tons of metal falls helplessly into the ocean. The rockets which carry it aloft won't be needed once liberated from the perpetual tug of gravity. Fuel tanks, rockets, man-hours, and meticulous attention to safety means that every shuttle mission costs $500 million. During the Cold War, scientific bragging rights were worth almost any cost. But today, space has a new, more practical role. The revolution in digital communication has brought the satellite from the hands of the few to an irreplaceable part of everyday life. By the year 2010, the number of satellites orbiting the Earth will increase tenfold, making access to space as much to do with the pocketbook as scientific achievement.
The cost to get into space is just too high. Today, it's about $10,000 for every pound that you want to launch to space. And what we're going to have to do is dramatically reduce the cost down to $1,000 and even below if we're really going to be able to achieve all the benefits that space systems can offer us.
The answer lies in a wedge-shaped machine that will take off under its own power, get to orbit, and return to fly again. It's called the Venture Star, tomorrow's link to space. The Venture Star will emerge from America's best-known, yet most secretive design team, Lockheed Martin's Skunk Works. It will pick up where the space shuttle left off. The key to the entire program is summed up in 4 words: single stage to orbit. The Venture Star's 7 unique rocket engines will carry it from sea level through the atmosphere without the aid of booster rockets or fuel tanks. It will reach space on its own, return to Earth, and be ready to fly again within 7 days. If all goes as planned, it will reduce the cost of getting to space by a factor of 10. It will carry satellites to orbit and provide the lifeblood of man and material to the new International Space Station. It may not be pretty, nor will it satisfy the whimsical ambitions of those futurists who want to see motels on Mars. But today, the Venture Star represents the most practical and immediate means of getting to space. The Venture Star is the culmination of NASA's search for an RLV, or reusable launch vehicle. Along the way, this search led them down several different paths. Unique among these was the DCX-A. When NASA laid out the ground rules for a reusable launch vehicle, the 2 most important requirements were that it take off under its own power and return safely to Earth. The 43-foot-tall DCX could not only take off under its own power, but it would land the same way, on its tail. The unique approach captured the attention of the U.S. Air Force, which named the cone-shaped rocket Delta Clipper. Then in the summer of 1995, the Air Force turned it over to NASA. The unmanned craft was extensively modified, renamed Clipper Graham, and then moved to the desolate missile range at White Sands, New Mexico. The first NASA flight came on May 18, 1996. All test flights were controlled from a trailer 1 mile from the launch pad. The first flight was routine until the landing. As the rocket touched down, a fire flared up, scorching its side. After replacing a damaged flap, the skin was scrubbed, resprayed, and flight tests resumed. The Clipper Graham was never meant to get into space, merely to demonstrate that a rocket-powered machine could take off, climb to a respectable altitude, land, then refuel, and do it all over again in a short period of time. This it did on its second and third flights. On June 7th, the rocket climbed to 2,000 feet, traveled laterally 560 feet, as seen here on the computer model, and then returned to Earth. Just 26 hours later, the Clipper Graham climbed to over 10,000 feet, moved across the range about the length of a football field before landing safely on the pad. The significance of the flights wasn't that the rocket performed flawlessly, but that the 2 flights were completed in just over 1 day. Unfortunately, this would be the high point of the Clipper Graham program.
Securing ground, flight crews ready.
The 4th flight came on the last day of July, 1996. At 15 minutes after 1 o'clock, the Clipper Graham fired up its engines. The flight was intended to last 2 minutes.
Launch and flight.
All engines up and running.
Out of 100 feet. Out of 500.
The takeoff was routine. After less than a minute and a half, the rocket peaked at 4,000 feet. It then pitched its nose over 60 degrees and began heading down the range.
Coming up on 50, looking good. Heading for the landing site.
Everything was going as planned. After traveling almost 3,000 feet laterally over the desert, the Clipper Graham began its descent. So far, the flight was a complete success. The Clipper Graham had achieved all test objectives and appeared to be heading for a routine landing.
Landing cue limit.
98 seconds into the flight, the computer ordered the landing gear to deploy. Then something went wrong. After landing, the rocket tipped over and burst into flames. Its internal water tanks couldn't contain the fire, and emergency crews headed toward the range.
First of all, I want to say we had a good flight until the landing. The vehicle flew the flight profile as planned. The flight profile was going extremely well. Everything looked real good. The problem came about 200 feet above the ground when 2 gear deployed, 1 gear came down slowly. The 4th gear did not deploy.
The Clipper Graham was completely destroyed. The culprit was a disconnected brake line on the landing gear's helium pneumatic system. Although the accident wasn't any fault of the design, the Clipper Graham program was shelved. Nonetheless, it was a major step toward cheaper, more accessible space travel.
DCX was essentially the first in this series of advanced space transportation systems looking at ways to reduce the operational cost and reduce the cost of going into low Earth orbit. So it demonstrated that you could flight test with a small number of people, you could turn it around between flights with a small number of people. So this demonstrated operational efficiency for advanced space transportation systems.
Way on gear, engine shutdown.
In his 1985 inaugural address, President Ronald Reagan spoke of a new Orient Express, which by the end of the decade would take off from Washington, accelerate up to 25 times the speed of sound, and reach Tokyo in under 2 hours. What Reagan was referring to was a highly classified project called Copper Canyon. It was then being funded by DARPA, the Defense Advanced Research Projects Agency. But the Copper Canyon plane was never really expected to fly from Washington to Tokyo. It was designed for single stage to orbit, part airplane, part spaceship. It would take off from a runway, achieve orbit, then land the same way it took off. Copper Canyon evolved into this, number 30 in America's proud family of experimental planes. As the design of the X-30 aerospace plane went public in the late 80s, it was touted as the shape of things to come. It stood on the shoulders of its experimental predecessors. It was a sort of ultimate X-plane, made possible thanks to breakthroughs in composite materials and digital processing. But propulsion was the real challenge. Getting from sea level to space with a single engine is the holy grail of aerospace engineering. The X-30 was indeed ambitious. It initially resembled the Concorde, but as it turned out, this look was more stylish than practical. As the program matured, so did the shape. The sleek pencil-like body was flattened, and the wings were all but removed. The X-30 may have been transformed into a flying shoehorn, but NASA and the DoD had an aerospace plane they could believe in. The purpose of the X-30 was to harness the power of a new kind of engine, the scramjet. Everything about the spaceplane has to do with the engine. Its very shape had a purpose. The squared nose and wedge-shaped body were designed to create smooth airflow for the difficult business of supersonic combustion. The entire X-30 aerospace plane would be built around the engine. The scramjet would burn on a mixture of hydrogen fuel and oxygen, which it scooped up from the atmosphere. Once in space, old-fashioned rocket power would take over. Not to be outdone by the Americans, a European consortium came up with a design of their own. But for a time, it was the X-30 which appeared to be the future of space travel. It was hailed as the next generation shuttle, perhaps even taking passengers to future space stations. It seemed that the X-30 was a space plane for the people, but the program's budget structure is more telling. With 80% of its funding coming from the Department of Defense, it was clear that the government had something else in mind. Exactly what is unclear. An aircraft capable of appearing over any part of the world in just an hour and a half could have made reconnaissance or ballistic missile defense a tempting option. Whatever the intention, the U.S. Air Force began to have its doubts, and in 1994, backed out of the program. On its own, NASA couldn't carry the burden, and the X-30 program faded, almost as quietly as it had appeared. Today, the X-30 aerospace plane has been reincarnated, not as a passenger plane to the stars, but an unmanned 12-foot research plane called HyperX. Dr. Scott Holland works at the NASA Langley Research Center in Virginia. His latest challenge is to help see the HyperX through its most difficult ride, going from concept to reality.
The HyperX project is designed to demonstrate net positive thrust from a scramjet in a flight environment. What it involves doing is taking a small-scale flight vehicle, in this case a 12-foot-long vehicle, boosting it to altitude, separating it from the booster, and then allowing the engine to ignite and demonstrating that the vehicle will accelerate.
Sounds easy enough. First, the 12-foot HyperX is mounted to the front of a Pegasus rocket, then dropped from the wing of an Air Force B-52. The rocket fires, taking the unmanned HyperX to 110,000 feet. Then the real test begins. If all goes well, the HyperX will break free from the Pegasus. Then the blistering force of the onrushing air will ignite the scramjet. The HyperX will accelerate, traveling over 7 miles in only 5 seconds before burning out. It seems straightforward. The catch is, a scramjet has never been tested in flight. Tucked within the bowels of the Langley Research Center is one of NASA's few operating scramjets. The exact design is sensitive. It's concealed from our cameras within a small metal chamber inside a hypersonic wind tunnel. Before the air enters the scramjet, it's compressed in what's known as an arc heater. The arc heater is adorned with a labyrinth of orange hoses. Some contain water for cooling, others pipe in gaseous hydrogen used to fuel the supersonic airflow. The compressed air is then forced into the scramjet's wind tunnel chamber at speeds exceeding 5 times that of sound. The scramjet may be the engine of tomorrow, but the idea is nothing new.
The ramjet requires virtually no moving parts. Incoming air is compressed simply by ramming the whole engine ahead at high speed.
The scramjet is really just a more advanced version of the ramjet, a technology that's been with us for over 60 years. Like common jet engines, ramjets provide thrust by compressing air, burning it, and forcing it out the back. The difference is, a ramjet has no moving parts. The air is compressed by the forward speed of the engine itself.
At the moment, the
ramjets require air to be entering at supersonic speeds. In the past, they've been tested on airplanes, rockets, and even the tips of helicopter rotors. The scramjet is the next step.
A ramjet requires the air to be entering at about Mach 2 or 3. And that's the minimum speed at which the momentum of the air can provide enough energy to provide the compression process. Now, a scramjet takes over from a ramjet around Mach 5, and the term scramjet is a supersonic combustion ramjet, and the air is not slowed down to subsonic speeds, but instead the combustion process takes place at supersonic speeds.
Scramjet is so simple. It's just like any other engine. To produce power, you have to compress the air, then you add heat, and then you expand, and in that cycle, you actually produce thrust.
This is one of the many hypersonic wind tunnels at the NASA Langley Research Center. Hypersonic is the term for the blistering speeds of Mach 5 and beyond. At one side of the tunnel is an enormous tank where air is compressed to over 200 pounds per square inch. On the other side is a massive vacuum. When the valves connecting them are opened, the compressed air screams toward the vacuum through a 31-inch tube at 10 times the speed of sound.
All right, I'm ready for 250, 450 when you are. Okay. Temperature come up now. He's pretty close.
The HyperX will eventually fly at Mach 10. At this speed, the friction of the air is enough to char its vulnerable leading edges. Before dropping from the B-52, models like this one will spend thousands of hours being blasted in NASA's wind tunnels. Airflow patterns, shock waves, and the searing effect of the air will be meticulously studied. This 3% replica is testing the interaction between the Hyper-X and its booster rocket, the Pegasus. It's one of the most difficult challenges of the program.
The model I'm holding here is a 3% model of a Pegasus with the Hyper-X on the leading edge. What this model is designed to do is to help us understand the forces that the vehicle will go through as the flight vehicle is dropped off of the B-52, then accelerated to the test point, and brings us to the point where we want to separate and take the free flyer away from the Pegasus so that we can begin our engine test.
The Hyper-X will separate from the Pegasus rocket at speeds exceeding Mach 5. This split-second event is the most risky part of the test flight.
There are two pistons that fire to separate the free flyer from the Pegasus to move it forward, and at the same time there are pistons that fire to rotate the lower portion of the adapter down so that we can minimize the possibility of recontact.
Computer models will let engineers study the airflow at hypersonic speeds and help predict what will happen during the crucial microseconds that the Hyper-X breaks free from its booster.
These are computational fluid dynamic, or CFD, solutions. This is that part that breaks down here, and this is a research vehicle. What we have right here is about 30 degrees rotated down. It creates strong shock waves. As it moves back, and I'll walk through it quickly to start with, you can see that the shocks move back with it. The disturbance on the research vehicle is less. At this point, that has rotated all the way around and has been assumed to break off.
If the separation goes as planned, the three flight vehicles will fly first to Mach 5, then to Mach 7, and finally to Mach 10. But the Hyper-X wasn't built to last. Each will succumb to the thermal extremes of hypersonic flight, but not before revealing the secrets of the scramjet, a stepping stone to affordable space travel, and perhaps the Orient Express of tomorrow. This wedge-shaped machine represents the next step in space transportation. It's called the X-33, and by the turn of the century, it will emerge from the shadowy design offices of the Lockheed Martin Skunk Works. The X-33 is known as an advanced technology demonstrator. Its purpose isn't to fly into space, but merely to pave the way. At 63 feet from tip to tail, it's an exact half-scale replica of the Venture Star, America's next-generation spacecraft. The X-33 will be powered by 2 rocket engines, 5 less than the Venture Star. A series of test flights will launch it to an altitude of 50 miles and a velocity 15 times the speed of sound. After each flight, the X-33 will catch a ride back to Edwards Air Force Base in California, aboard a NASA 747. The longest of these flights will be after the X-33 makes its third and final hop to Malmstrom Air Force Base in Montana. The entire reusable launch vehicle program is a cooperative agreement between NASA and the builders. The key to the program is summed up in 4 words: single stage to orbit. For years, it has been the most difficult barrier on the road towards greater access to space.
Single stage to orbit is so challenging because you carry everything with you. You don't drop off tanks, you don't drop off rockets. Every pound that's in the vehicle has to go all the way to orbit.
The answer is a unique rocket engine called the Aerospike. Conventional rockets, like the boosters on the space shuttle, burn most efficiently only at specific air pressures. At low altitudes where air pressure is high, the rockets work best exiting in a narrow stream. But as the rocket moves higher, a wider exhaust plume is needed to compensate for the drop in air pressure. In the past, NASA overcame the problem by piling on all the rockets needed. After each rocket pushes through a given altitude, it burns out, falls to the Earth, and the next one takes over. The linear aerospike engine is shaped like an upside-down bell. The rockets are positioned in 2 rows along the top. As the rockets fire, pressure causes the exhaust to cling to the sides of the engine. But as the engine pushes to higher altitudes, the natural decrease in pressure allows the exhaust to ease away from the engine, automatically changing the shape of the exhaust plume. The idea isn't new. During the early 70s, it was suggested to power the space shuttle, but NASA rejected it as too risky. The X-33 will be the second machine to carry the aerospike engine. The first is sitting in a hangar at NASA's Dryden Flight Test Center in California. It's a sleek veteran, the SR-71 Blackbird. Mounted to the back is a section of the X-33 containing a scaled-down aerospike engine. Like the Blackbird, the partial spaceship bears the unmistakable mark of the Skunk Works. The SR-71 was chosen to test the aerospike because of its famed reputation for reaching extreme altitudes. The Blackbird gives the engineers about the closest thing they can get to leaving the atmosphere. The Venture Star will be pushed aloft by 7 aerospike engines. The setup not only provides single stage to orbit, but it's safe. The failure of one of the shuttle's booster rockets spells disaster. But the Venture Star's line of 7 engines can deal with such a problem. If an engine quits, its opposite number automatically shuts down. The remaining engines power up, and Venture Star stays on course. Another advantage offered by the Venture Star is its simplicity and easy turnaround. On the space shuttle, the protective ceramic tiles need to be checked and, if damaged, replaced. A process which takes over 17,000 man-hours for every mission. The Venture Star won't have this problem. Its outer skin will be a metallic thermal shield, rugged enough to withstand 100 searing re-entries. But when the Venture Star returns, it can't simply float toward Earth. It needs to maneuver its way down, or else it will skip off the dense air of the atmosphere like a rock off a pond.
This vehicle flies from 20,000 feet per second down to landing speeds. So they have to be able to make certain maneuvers. Primarily, they must rotate about this wind coming at them this way, sideways, so that they fly sideways rather than up and out of the Earth's atmosphere, or they're in trouble.
The boat-like hull of the lifting body is the optimum design to survive re-entry. But during landing, it's the Achilles heel. A lifting body doesn't provide lift nearly as well as the wings of an airplane. It can also be difficult to control, especially if it begins to roll back and forth. But the pitfalls of landing are mitigated by one important factor: weight. Without fuel, the Venture Star is only 1/8 its takeoff weight. Unburdened by payload, the buoyant spacecraft can land on an 8,000-foot runway, shorter than most major airports. Once the Venture Star lands, the challenge is to get it checked out, loaded, and ready to fly again in just 7 days. The key to the quick turnaround is a revolutionary launch and recovery pad. These pads are much smaller than the vast complexes used by the shuttle. They're designed for convenience and a small maintenance staff. For example, instead of taking the Venture Star to the hangar comes to the Venture Star. One of the Venture Star's strengths is cargo capacity. A lifting body has a vast amount of internal space. A fully loaded Venture Star will weigh as much as 2 747 jumbo jets, even though its length and width are roughly equal to the much smaller 757. The cargo is checked and sealed within a large package about the size of the containers pulled by a standard 18-wheeler. The package is brought into the hangar and then lowered into the Venture Star's 15 by 45-foot cargo bay. For flights to low Earth orbit, the Venture Star carries up to 40,000 pounds. The other 2 million pounds are reserved for the liquid hydrogen and oxygen needed to get it there. The amount of fuel and cargo aboard such a light spacecraft makes the Venture Star the aeronautical equivalent of a 20-pound bicycle carrying a person who weighs 200 pounds. When all's clear, the hangar pulls away. The Venture Star is already sitting on the launch pad. Without booster rockets or external fuel tanks, the unwieldy job of assembling a launch package is eliminated. The Venture Star is ready to fly. The Venture Star will be a cooperative effort. NASA takes on the high-risk technologies, while industry is responsible for building it. The contractors don't make a profit. The Venture Star will be built at cost. But if it works, they'll make money launching it. The reason for this kind of thinking is simple. A revolution in digital technology has changed the way we communicate. Satellites are already being used to connect digital cell phones or provide movies to the home. Global positioning satellites provide real-time maps for rent-a-cars and precise locations to stricken boaters. Today, we're seeing only the beginning. As we grow ever more dependent on satellites, the Venture Star may be a cheap way of getting them to orbit. NASA and private industry hope to reduce the cost of putting satellites into space from $10,000 a pound down to only $1,000. When a company wants to launch a satellite, they'll rent space aboard the Venture Star. It's a lofty goal, but if it works, the Venture Star will do more than deliver satellites. In the decades to come, NASA's going to need to go to space more often. It will be an important shareholder in a permanent manned oasis, 248 miles above the Earth. The United States, Russia, Canada, Japan, and the members of the European Space Agency are combining their efforts to build a truly international space station. When all the final modules, panels, and trusses are attached in 2002, the space station will span the size of 1.5 football fields. Each of the laboratory and habitation modules are about the size of a school bus. Over an acre of solar panels will provide 112 kilowatts every 90 minutes, the length of time it takes to orbit the Earth. A cupola gives the astronauts a 360-degree view all around. When work needs to be done outside the space station, the cupola becomes the command center, letting astronauts watch and communicate with the spacewalkers. Aboard the space station, astronauts won't need as much sleep as usual. The body does less work when not fighting gravity. An average American plows through 160 gallons of water per day. Aboard the space station, astronauts will use only 8, almost every drop of which will be recycled. Although the space station is designed for self-reliance, resupply craft will be a welcome sight. As the American Space Shuttle and Russian Soyuz rockets begin to show their age, round-trip visits to the space station will be handed over to the Venture Star. Crew members will ride in a passenger module which fits snugly in the cargo bay. When the Venture Star approaches the space station, the cargo bay doors will open, and a pre-programmed flight control system will guide it into the docking module. Many communication satellites dwell in low orbit above Earth. To reach the space station, the Venture Star will need to go much further, limiting its capacity to about 20,000 pounds. The space station will be the largest manned object ever to orbit the Earth, but it may not seem so big after 6 months. For tired astronauts, the Venture Star may be a welcome way home. As one group arrives, another will leave, but life on the space station will continue year-round.
The new International Space Station will allow us to have a 24-hour, 7-day-a-week, 365-day-a-year manned space activities going on for all sorts of areas of research that really dramatically affect things here on Earth.
Without gravity, scientists will not only unearth new discoveries, but improve on what we already know.
Extremely high-quality chips can be manufactured in the zero-G environment. Likewise, medical research can be conducted, unique things that look at the way bones grow, for instance, and repair themselves. It can, again, be conducted on the space station in a way that can't be done on the ground. So that continuous manned presence in space on the space station will allow dramatic advancements in our technology really across the board in all sorts of areas.
Like a ship at sea, the space station sails alone through an unfriendly environment. If something happens, it too will need a lifeboat. This is the X-38, the prototype for such a spacecraft. It's constructed under a NASA contract by Burt Rutan. Burt designed the world record-breaking Voyager. NASA calls their lifeboat a Crew Return Vehicle, or CRV. It will carry up to 6 passengers lying on their backs. During any medical or mechanical emergency, astronauts can be on their way to safety within 3 minutes. As the CRV moves away from the space station, a small rocket, appropriately called the de-orbit engine, is fired, pushing the astronauts earthward. What happens next is well understood. The emergency CRV is closely based on Air Force lifting body aircraft flown during the mid-60s. The heat of re-entry is spread evenly along the CRV's rounded underbelly. For an astronaut who has been in space any length of time, landing is never easy. Bone and muscle are weakened by a prolonged lack of gravity. When they return, their body has trouble dealing with their own weight, much less a punishing impact with the ground. To soften the blow, the CRV will automatically deploy a steerable parachute developed by the U.S. Army. The spacecraft will touch down on skids rather than wheels. For those aboard, the 2-hour ride home may not be comfortable, but it beats the alternative. While the Venture Star sits on the horizon, dreamers and aerospace engineers alike are already looking beyond. New designs and untested propulsion systems will be needed to provide true breakthroughs in space travel. These technologies are too risky and far-reaching for industry, so NASA's Space Transportation Program is leading the way. The main goal of the program is to carry people, satellites, and cargo to Earth's orbit and more distant destinations like the Moon. Before the turn of the century, NASA will explore computer models of exotic designs. But like the Venture Star, the key to any aerospace revolution is in the engine. The dreams and ideas of tomorrow appear to draw from the whimsical prose of science fiction. Most are classified with names like pulse detonation, fusion propulsion, antimatter, and gravity modification. For some experts, it all seems a little too much, but the space transportation program is significant not because it's going to revolutionize the way we get to space, but because it will change the way we think we can get to space. Only then can we make the breakthrough needed to open the final frontier. Almost 400 years ago, Galileo made the first telescope observations of Mars. Since then, man has been fascinated by the red planet. Finally, in the summer of 1997, we all visited Mars. Not through the eyes of intrepid astronauts, but through the camera lens of a 2-foot robot called Sojourner. The event has rekindled an old idea: to take the next step, sending man to Mars. Dr. Bobby Braun worked on the Pathfinder team.
If Pathfinder had failed, it would have been a catastrophic loss for all of us that had worked on the mission for 5 years, but there would have been no loss of human life. As soon as you take that step to a human mission, the complexity of it just goes way up.
In 1953, Wernher von Braun published The Mars Project, a work which detailed mathematical tables for a manned mission to Mars. With the success of Pathfinder, von Braun's work has been taken from the shelf, dusted off, and plans to put people on Mars are beginning to take shape. A manned flight to Mars won't happen all at once. It will be a step-by-step process which has already begun with the Pathfinder. A series of unmanned capsules will be blasted toward Mars as early as 5 years before the people. By the time the astronauts arrive, much of what they need will already be there. As the astronauts depart, most of their cargo will be the fuel which sees them through the journey. The problem is getting back. Carrying fuel for a round-trip journey is unwieldy and expensive. To make the trip possible, they'll need to make fuel on Mars. Using the Martian atmosphere and a few key ingredients brought from Earth, the astronauts won't need to bring fuel for the ride home. Even so, the amount of cargo needed to support a human visit to Mars will amount to the largest journey ever taken outside the Earth's atmosphere.
It was about 200,000 kilograms of gross weight on that launch vehicle that took Pathfinder to Mars, and we only put 24 kilograms of payload on the surface. That would go up by a factor of 10 to 100 for a human mission. And of course, we're putting a lot more than just 24 kilograms on the surface because we're putting several people, plus the supplies, plus a rover that's more like a car, perhaps.
The kind of engine which will take man to Mars is still under debate. Nuclear propulsion is the most efficient, but firing an atomic reactor through the atmosphere on a pillar of volatile rocket fuel doesn't go over well on Earth. In the years to come, debate will continue over whether the engine should be a conventional rocket, nuclear, or something else. Whatever the decision, it's going to be a long trip. It could take anywhere from 6 to 18 months, depending on the number of people, trajectory, and even the year that it leaves. Some engineering studies even suggest that because of the immense risk, the crew should be kept to a minimum of 4. During the journey, the real threat comes from prolonged exposure to galactic radiation. The next problem is the descent to Mars. In 1997, the Pathfinder entered the Martian atmosphere without a hitch. But as Dr. Bobby Braun can explain, putting a robot down is one thing. Safely delivering people is entirely different.
Pathfinder pulled about 16 Gs during the entry there at Mars. If you think about people traveling through space for a year, year and a half on the way to Mars in a zero-G environment, they're not going to do too well pulling 16 Gs. So we need to shallow out the entry, essentially, to spread out that G pulse, maybe get it down to 3 or 5 Gs. That requires a different shaped vehicle, one that has a little bit more lift and flies a bit more like an airplane than like Pathfinder, which essentially just fell like a rock through the atmosphere.
The landing will be carried out automatically by a pre-programmed onboard computer. Some planners have even suggested not bringing a pilot, saving the seat for a geologist or chemical engineer. Whatever the makeup of the crew, it's vital that they land in exactly the right spot.
To send people to Mars, we're going to send a few cargo ships first. What would be nice is if the first cargo ship could land, say, somewhere in this room. The next cargo ship could land in, just a few feet away. And when the people came, they were just several more feet away, so everything could just be plugged together, and you'd have your little base camp. What you don't want to do is have one cargo ship, 100 miles to the east, and the other cargo ship 100 miles to the west with the people in the middle.
On the Pathfinder, precision landing wasn't an issue. The cocoon-like package was dropped off in roughly the right place before bouncing to a final resting spot.
Pathfinder's landing ellipse was about 200 kilometers by 100 kilometers. That's roughly the distance from Los Angeles to San Diego. And you can see that if we set down 3 ships that all had to work together between LA and San Diego, that when the people got there, there'd be a lot to do.
The people will have a lot to do anyway. After making their triumphant first step, the first order of business is to begin making the 3 things necessary to survive: air to breathe, water to drink, and fuel to get them home. The Martian atmosphere is almost entirely carbon dioxide. Oxygen is produced by breaking down the ambient atmosphere with a CO2 reduction unit. To make fuel and water, the only ingredient the astronauts need to bring is liquid hydrogen. The rest is simple chemistry. A processing unit combines the hydrogen with the atmospheric CO2, producing methane and water. The amount of fuel produced is more than 18 times the amount brought from Earth. 12 tons of it will power the rovers used to explore Mars. The rest is needed to get home. Since the astronauts' arrival, their ride home has been loitering around Mars in an orbital parking lot. Now comes the time for the crucial rendezvous. The orbital link-up is the final challenge of a momentous journey. The closing of another frontier. It won't be cheap, and it won't be easy. But one day, it may be a reality.
I'm actually very confident that in my lifetime I'll see people going to Mars. I used to think when I was younger that it would be me, but I'm not confident of that anymore. I actually think that people that are in school now, whether it's in junior high perhaps, or high school, that some of those people will probably be the first to create footsteps on Mars.